Okay, so we have homework 4, energy balance. Okay, and the question simply states that water from a 3-meter tall by 30-meter diameter holding tank flows vertically down a 7-meter length of 1-meter diameter pipe into the bottom of a massive gold-plated jacuzzi through a 10-inch diameter horizontal nozzle. The water depth in the jacuzzi is kept at 1 meter by pumping water back into the tank. Okay, and the energy conscious king wants to know how much power the 100% efficient pump requires, and if the pump is perfectly insulated and transfers no heat to the water, is a chiller necessary to keep the water at the same temperature? Okay, so two questions. We need to find power, and then do we need a chiller? Yes or no? Okay. All right. And so to start, we can start by drawing and kind of showing what the question is basically stating. So we have a tank with water in it, and it's at a 3-meter level, and that tank is releasing water down this pipe that's about 7 meters from the bottom of the jacuzzi. Okay, and that's the bottom of the jacuzzi, and the water is going, and then at some point here there's another pipe that's hooked to a pump. Okay, this is a pump. Okay, and the pump just pumps the water back into the tank, again keeping that level in the jacuzzi, the water level in the jacuzzi, at 1 meter. Okay, and so we're asked to find the power this pump requires to do its job. Okay, so to start, we know that to be able to find power, we have to find the flow rate of the water that's coming up the pump, and simply so the power is going to be some non-flow work times that the flow rate. Okay, and to be able to do that, we can find the flow rate of what's coming down, and that's simply our flow rate of the water on this end. Okay, so we can start by I guess recalling something. So if we have some sort of tank with water in it, and it's got a 0.1 here and a 0.2 here. Okay, we know that the pressure, if the pressure here at 1 is equal to the pressure at 2, then from energy balance, that V2 is equal to the square root of 2 times gravity times this height. Okay, and then you could find the flow rate of the water by simply multiplying this velocity of the water at this point coming out times the cross-sectional area, gives you that flow rate, gives you flow rate Q2, and knowing velocity, we could simply just make Q2 equals to A2 times square root of 2GH. Okay, and A2 is simply something like pi r squared. Okay, but we'll get back to it. So now, back to our question. Okay, so we could create some sort of points to kind of imitate this example over here on the right. We could create point 1 over here, and then I'm gonna put my point 2 down here at the bottom. Okay, and that's just at the bottom of the jacuzzi. Now you could put this point 2 at any point. You could put it at the top of the water level. It's not gonna change, and this is why. So we know that P2 minus P1, okay, all over rho plus gravity times the change in height, which is that, so Z2 minus Z1 plus V2 squared minus V1 squared all over 2 is equal to 0, okay? Water is flowing down. So the velocity here, 2 minus V1 is equal to 0. So V1, since it's on the top of the water, and this tank it's got such a big diameter that V1 is very, very small. It's negligible. So we're gonna assume that's 0, okay? And then P1 as well, it's on the surface, which means it's again gonna be 0 as well. So that goes out the window as well. So we have P2 over rho plus gravity times the change in height plus V2 squared over 2 is equal to 0. Okay, and P2 is simply rho times gravity times the change in height plus the gravity times the change in height. All right, plus V2 squared over 2 is equal to 0. Now, if P2 is rho over GH, that means that rho goes away, and then we know that this height, again, that's our water level in here for the jacuzzi, is 1 meter, so we have 1g, okay, and then we know that our difference in height is 7 and 3, so minus 9 times minus 9, no, 10, 7 and 3, that's 10, minus 10, my bad, plus V2 squared all over 2 is equal to 0. So this minus 9g, okay, plus V2 squared over 2, basic algebra, V2 is basically square root of 18g, okay? All right, so we found our V2, okay? Now, to find our Q2 is simply A2 times V2. What's A2? A2 is pi r squared. Okay? What's r? Radius is diameter over 2. In the question, we're given that our diameter is 10 inches. So, radius is gonna be 10 inches. Okay, we're gonna put this into meters. So over 1 times 1 foot over 12 inches times 1 meter over 5.28 feet. This over 2 will give us the radius, which is about 0.127 meters. Okay, that's our radius. All right, I'm just gonna keep Q2 as simply pi r squared times square root of 18g. So we will replace that V2 back in here, and we're gonna keep the r as a variable for now, just to keep things a bit more compact. Okay, now, all right, we found our flow rate on this side, which means we can come here and with our power equation of the non-flow work over some mass times the flow rate over here on the other side that's going up, which is simply the volumetric flow rate of water, and to do that, to turn this Q2 into our flow rate, we just simply have to multiply it by the density of water. Okay, and that means Q2 times density of water Therefore, we have something like this section just simply becomes density of water times pi r squared times square root of 18g. Okay, now we need to find this. Okay, and to do that now, we're gonna have to do the same thing we did for this question for the first part to find Q2. And we could create points. We'll create a point here. We call it 5, and we're gonna start on the surface. We're gonna have our pipe start from the surface of the water. Again, it does not matter which way where you put it. You end up with the same answer, because if you look back at here, like had we put our point on the surface, that means P2 would have been 0 and our height would have been 7 minus 1, giving us 6 over here, plus 3, 9. So you would have ended up with 18G as your V2. And the reason it does not matter is because the amount of potential energy you gain from increasing your pipe back into the water, you counter it by the pressure increase. So your pressure here is less than the pressure at the bottom of the jacuzzi. So you lose that energy because the pressure increase once you change your pipe. And same thing happens here. Okay, so you increase this section, but the same effect happens opposite on this side of the equation. Okay, so back to our problem. Now we know that P2. Okay, so we'll have P5. P5 minus P4 all over rho. Okay, plus gravity times the change in height Z5 minus Z4. Okay, and our V5, we could add it all in there. V5 squared minus V1 squared all over 2. Now it's not equal to 0 because we're doing some work with the pump, so it's gonna equal to the non-flow work per mass. Okay, kilogram. Right, and again, the velocity is, our diameter is so big that that velocity is simply 0. It's ignored. It's negligible. Same thing. So we lose that side of the equation. Our P4 is on the surface, so that's 0. P5 is the same thing on the top of the water level atmosphere, so that's 0 as well. So we lose this side of the equation. And now all we have left is the change in height times gravity, which is simply from here to the top, 6 plus 3, which is simply 9. Okay, so we have 9G is equal to the non-flow work per mass. All right, so we have that now. So we can bring it and put it in our power equation and get something like this: pi r squared times 18G. Don't forget the density of water. Don't forget the density of water, and then times this 9G. Okay. And when we do that, when we replace our variables and variables for r, which is right here, we get density of water. We all know is so by the way, that's our power equation. Sorry, my paper keeps moving. There you go. So we could just replace the variables. Density of water is about 1,000 kilogram per meter cube. We multiply that by pi. We put our radius in there, 0.127 meters squared. And then we add the square root of 18 times gravity. That's 18 meters, by the way, 9.8 meter per second squared, because that's height, that's from height, so therefore it's 18 meters. Same thing here, 9 meters, it's height. And then we multiplied that by 9 meters times, again, 9.8 meters per second squared. And all this, when you put it in a calculator, it gives you around 59,000 kilowatt. And then are we asking if we need a chiller or not? And the answer is yes, we do need a chiller, even though it might seem like we don't, but we do, because of the amount of work that's the power that's put into our water, our whole system. It's got to come out somewhere, it's got to come out somehow to maintain the same temperature of the water. So yes, we need a chiller. Okay, to retract the equal amount of effect that power had on the temperature of the whole water. So there you go. Thank you.